All right, we'll get started then. I posted homework assignments full five, whatever homework assignment it is. Okay, so I posted that up there. It'll be due on Wednesday before Thanksgiving, and then that way you can enjoy your Thanksgiving weekend all with your family or whoever you're going to be with. Yeah, okay. So today we will continue our talk with non-parametric bootstrap and the Jackknife. Okay, so Jackknife again is a resampling method where we, maybe I'll write this in here, big picture behind Jackknife. Where we remove each of the data points one by one. One by one, and or I should say one at a time, and recalculate the statistic, the desired statistic, based on the remaining n-1 data points. Okay, so we covered we introduced Jackknife a little bit already, and we can use it to estimate bias. We can use it to estimate standard error also. Okay, so if we're looking at the law school data set, data parentheses law serves as a random sample of 15 randomly selected schools from that population of 82. Okay, and to perform Jackknife, we say, okay, for I and 1 through 15, basically how many data points we have, we are going to calculate the correlation by removing that one row out of the data set. Okay, and so we're saying basically with the 14 remaining LSAT scores and the 14 remaining GPA, calculate the correlation. Do that for, remove data point 1, remove data point 2, remove data point 3, all the way up to data point 15. So at the end, we will have 15 values in theta.jack. So I can, here, let me clear out my environment here. So we can run each of these things. So when I'm done, theta.jack will have 15 values in it. And so we can see how the values vary. If we remove the first data point, it really increases our estimate of the correlation. Okay, whereas other data points, if we don't remove them, it doesn't seem to affect it very much. Okay, so let's take a look here. And to calculate the bias, the formula for that is n-1 times basically the difference between each theta hat and the mean. The mean of all the Jackknife estimates, all of these, the mean of these 15 numbers, minus the correlation or the estimated statistic based on the full data set. So the full data set, if we use all 15 data points, we get theta hat, and then we just take the average of these 15 data points and take the difference. Okay, and then so here we get bias to be negative 0.0647. Okay, we can do the same thing for the standard error. So because I've already run the Jackknife sampling, all I have to do is just plug in the quantities that I have to get the standard error of our Jackknife. okay, or the estimated standard error of the correlation. Okay, so we're trying to estimate the standard error of the correlation, and that's given by this formula. And so we take each of the 15 values and we subtract off the mean of these 15 values. Okay, so it's essentially we're getting like sum of squares theta jack. Okay, so we're getting sum of squares theta jack, and then we're taking the mean of those and then multiply that by n minus 1. Okay, and so when we do that, we get a standard error, estimated standard error of 0.1425 or whatever. All right. Does this feel okay, Jackknife? It's just a resampling method where you're just removing one piece at a time. Okay, and then so now we have this thing called Jackknife after Bootstrap. Okay, so just keep in mind what Bootstrap is. Bootstrap is random sampling with replacement of the sample that we have. So we have a sample of 15 data points or whatever it is. We take samples of 15 from that sample of 15. Okay, we're taking random samples with replacement of size 15 from that sample, and we do this over and over and over again, hoping that it will provide insight about the population. Okay. Oh, there were some questions about, why does how does this work? Because it just seems like there's no way this this method could work. So there are I posted a couple papers on CCLE. This is oops. So this one comes on Stack Exchange. Okay, you guys know about Stack Exchange, right? It's like I get half all of my answers from there also. Okay, so anyway, this is a pretty good. There's some pretty good explanations in here. So they have this highly voted answer is just kind of this very high level overview, and then down here, even though it only has 22 upvotes or whatever, this is actually pretty good. This one's a little bit more mathematical. And then if you want to get into even more math, there is this paper, which uses Edgeworth Expansions, which don't ask me about them because I don't really know. Well, so Edgeworth Expansions are just kind of this, it's a series that approximates a probability distribution, but other than that, I don't really know how they work. That shows that through this, via Bootstrap, asymptotically, it approximates the distribution that you're looking for. So anyway, those links are there, okay? And then here's your homework 5. Okay, so anyway, this is kind of the idea behind Jackknife after Bootstrap. Okay, so we have a sample. We're trying to estimate the parameter of a population based on our sample. Okay, the standard error, and this is just in general, not just Jackknife and Bootstrap. The standard error is a measure of the variability in our estimate, right? So, you get some kind of sampling distribution on that sample statistic. The standard error is a standard deviation of that sampling distribution. Okay, and so we can do Bootstrap to estimate this standard error. So even though we don't know what the population looks like, and thus we can't figure out the sampling distribution directly, we can perform Bootstrap to get to estimate the standard error. Okay, but this, I think on Monday we kind of demonstrated this, that that these Bootstrap standard error estimates do depend on the sample that we have. Okay, depending on which 15 data points from the population end up in our sample, our standard error estimates will vary. Okay, so you could do 200 or 2,000 replications of Bootstrap and you'll get something in the same ballpark, but just changing which of your 15 data points exist in your sample has a pretty big impact on that estimate of the standard error. Okay, so what we can do is then we can get an idea of the standard error of the standard error estimate. Okay, so that it feels funny saying that, but because we saw that this from Bootstrap, the standard error estimate has variability in of itself, we can get an idea of the standard error of the standard error. Does that make sense? And so we use Jackknife for that. I've seen no reactions. I'm assuming we're good with this. Okay, so here's just a very small example. What is it? Did I do 200 or 2,000? No, 2,000. Okay. So let's say we have a sample of 8 data points. Okay, and we create 2,000 Bootstrap samples. And so for each Bootstrap sample, we calculate an estimate of the parameter, right? And then we take the standard deviation of all of those estimates, and that's our estimate of the standard error of that statistic. Okay, and then we perform Jackknife. So one by one, we remove one at a time, we remove one of the 8 data points. Okay, and so let's say we remove data point 1. Okay, this creates a subset of the 2,000 Bootstrap samples. Okay, so let's say in the 2,000 Bootstrap samples, let's say 300 of them made use of data point 1. Okay, so when we do Jackknife and we take out data point 1, we take out those 300 Bootstrap samples, and then so we have the remaining like 1,700 Bootstrap samples with their corresponding theta statistic, and with this remaining 1,700 we get the estimate of the standard error. Okay, and then we move on to data point 2, and let's say 400 samples happen to contain data point 2, so we remove those 400, and with the remaining 1,600 data Bootstrap samples, we create another estimate of the standard error. Okay, and so we do this for all 8 data points, and so we will have 8 different standard error estimates that depend on whether we've removed data point 1, 2, 3, or data point 8. Okay, and so we have 8 standard error, 8 different estimates of the standard error, and then we take the standard deviation of those 8 standard error estimates. Well, we basically apply the Jackknife formula for the standard error here. Okay. Is that okay? Sure. Yes.
Why would this be equivalent to the standard deviation of the standard error for Bootstrap samples?
It is or is not?
Why is it equivalent?
So yeah, we're getting. Wait, why is this equivalent to the standard deviation of the? I'm sorry.
I don't get that part. So.
This part, or okay. So the idea behind Jackknife is, again, we're just going to remove one data point at a time based on what's remaining. We can get an idea of kind of how much the variation depends on individual data points. Okay. All right. So let me just see if I can explain this another way. Okay. So from Bootstrap in of itself, we get an idea of the standard error, right? That part's okay. Okay. But what we saw was that the standard error based on Bootstrap depends very much on the data points in our sample. That's correct also, right? Okay. And again, we don't have access to the population, but we want to know, kind of get an idea of how much the standard error depends on our sample. Like how much, if somebody else drew another sample and they estimate standard error via Bootstrap, how much is that standard error estimate going to differ from ours? We kind of want to get an idea of that. So we want to get an idea of kind of the standard deviation or the standard error of our standard error. And so Jackknife allows us to get an idea of that.
And you can repeat this process infinitely.
You can say, you know, right, can I get a standard error of this standard error estimate? And yeah, that's true. I guess, you know, people thought that this is a decent thing to do, but yes, you could apply this and continually get more, do it again and again, but we kind of just stop here, okay? So so we'll look at this data set called patch, okay? And it's included in library Bootstrap, okay? And so patch, if we take a look at it, it just has 8 data points. And these are like, they measured some hormone level under placebo, the hormone level when they applied the old patch, and the hormone level when they applied the new patch. And they just kind of want to get an idea of how much of a difference is there between the old patch and the new patch. And so, so Z is the difference between placebo and old patch, and Y is the difference between old patch and new patch. Okay, it's new patch minus old patch. Z is old patch minus placebo, I believe. And so what we want to do is just kind of get the ratio between Y and Z. This is what we're trying to estimate. Okay, so so we run these commands, and there's 8 of them. We're going to just extract out Z and Y. Okay, we will do 2,000 replicates, and we're going to create a spot to store our 2,000 replicates. Okay, and then I'm going to build an empty matrix. This matrix has 2,000 rows and 8 columns. Okay, and each row represents when I do my Bootstrap sample, which data points did I select? Okay, so the very first time I run this, you know, I selected data point 656252827, and I'm going to store this as row 1 in this indices matrix. Okay, and so this way I can see, you know, when I pull out data point 1, I can say, did my first Bootstrap sample include data point 1? And we look at it and we say, no, it did not. Okay, and then when I pull out data point 2, I can say, did my second Bootstrap sample include data point 2? And did my first Bootstrap sample include data point 2? And we say yes. When we remove data point 3, we say, did my first Bootstrap sample contain data point 3? We say no. Okay, so this way, by keeping track, so for all 2,000 Bootstrap samples, you know, we're going to keep track of these indices, okay? And that way we can go back and see if each sample includes a certain data point or not, okay? So what I'm going to do is just build a loop from basically 1 to 2,000. We're going to take a sample of 8 data points with replacement. We subset our Y and our Z, and then we take the ratio between the mean of Y and the mean of Z, because that's what this is the sample statistic that we're going for. Okay, so we do this, the mean of Y and the mean of Z, and we store that in theta sub B for our Bootstrap theta estimates. Okay, and then we also keep track of the indices that we selected. I goes into our indices matrix. Okay, and then and we run it, and it's done. Okay, so right here we can get an estimate of our standard error. We can just say, what's the standard deviation of all of our Bootstrap numbers, and we get this value. Okay, so this is kind of this is our estimate of the standard error behind theta b. We can ask, what is our average theta b? This is probably again, this is the value we get, but you know, we want to know, is this standard error you know, any good? And so we want to get an idea of the, you know, standard error of this number itself. Okay, so we're going to do the jackknife portion now. Okay, so for the jackknife, because there's only 8 data points in our sample, my end result for SE Jack, the standard error for Jack, there's only going to be 8 values here. Okay, and so we're going to run a loop, and it's only going to run 8 times. I'm going to create a function called keepers. Okay, and what keepers does is it takes it's going to take the row of indices, and it's going to say, are any of them equal to I? So are any of them equal to 1? Okay, or are any of them equal to 2 when it runs around the second time? Okay, and if any of them are equal to 1, it's going to return false to say, basically, don't keep these. All right. And then what we're going to do is we're going to take this function keepers, and we're going to apply it. So the apply function, basically you take a matrix and you apply a function to either the rows or the columns. So in this case, we're going to take the indices matrix, which keeps track of which data points were selected for each sample, and we're going to apply it to the rows, which is margin equals 1, and then we're going to run through keepers. So, you know, on this one, it's going to go through and it's going to just say, are any of these k values, these values in k, equal to 1? And it's going to come back and say no. So the because of the exclamation point, it'll say the opposite of no is yes. So are we going to keep that? Yes, we keep that. Okay, and then what we then do is we subset our theta b. Remember, there's 2,000 values in here, and keep will be as 2,000 trues and falses based on whether that sample has data point 1 or not in it. And then so we subset theta b, and we take the standard deviation of the remaining thetas there. Okay, and we store that value into the standard error from our jackknife into position 1, and then we repeat this for all of the data points in our data set. So we're removing data sets one piece at a time. Does this all make sense? We're all good here? Okay, all right, so it's done, and we can see, you know, here are the so we can see how the standard error changes as we remove different data points. Okay, so the standard error based on all 2,000 jackknife sample, or not jackknife, 2,000 bootstrap samples is 0.104, and we can see that if we removed, you know, the first data point, the standard error estimate goes up. If we remove the second data point, the standard error estimate goes down, and so on and so forth. Okay, so we get all these things, and then basically we're going to kind of ask, what is the it's not exactly the standard deviation of these numbers, but we apply this jackknife formula to it, okay, to get the standard error based on our jackknife. And it says the standard error estimate of this standard error estimate is 0.03. Okay, so it's the standard error of the standard error. And that's Jackknife after Bootstrap. Is that okay? So all of this code is written. I'll post this markdown file online. Okay. Jackknife after Bootstrap. Okay, so there are we have functions that exist in libraries. Okay, so there's library boot. Okay, and we can use this to basically do the same things that we did before. So far, all of our bootstrapping has been done. Okay, so when we do the bootstrap, we kind of did it ourselves. We just said, this is how you're going to find, do the sampling with replacement and keep track of them all, and then get your number that way. Okay, you can use library boot. Okay, and so we'll go back to our law school data set where we had 15, and to use library boot, you have to write a function to keep track of the statistic that you want information on. So in our case, we want statistic on the correlation, so we're going to just name our function R, but if you want to call this correlation or whatever, you can do whatever, you can name it however you want. Okay, this function that's going to return the statistic that you want has to accept two parts. Okay, the first is the data, and then the second part is the index. Okay, and that's just how the boot function works. Okay, and so probably one of your first lines in the in your code is subset the data based on the index, and you're just going to write it kind of like this: data index comma in brackets, and then we're going to store that as D. Okay, and then so once now you have this kind of the data that you're working with, then you can calculate the statistic that you want. So in our case, we want the correlation between the first column and the second column in our data. Yes?
Would index be a vector?
Index is, yes, index is a vector, but it's a little bit funny, and it's like a vector of the bootstrapping. So when it runs bootstrap, or when it runs boot, it generates the index of basically this thing. Okay, it tells you like which data points to select. So the index is a vector of basically the data points that it has selected. Okay, so when you run boot, it looks at data law and it says, oh, there's 15 rows in there. Okay, and then so when I'm running this, I'm going to take a random sample of 15 with replacement. Okay, and then it returns back an index, or so index would be the kind of the 15 rows that it has selected, and then so we're going to subset our data based on that. Okay, and then so now that we have that thing, then we calculate the correlation between the first and second column. Okay, so this function R will return our will always accept the data and the I guess index or indices. Maybe that's a better. I guess I can make that plural. Okay. All right, and then so I'm going to load library boot. Okay, and when you run the boot command, you just supply it what your data is. So we're going to use law, which is our 15 sample of 15 law schools. The statistic that we want, you give it the function, and then 2000 will be how many replicates we do. Okay, and we're going to store this as a Bootstrap object. Okay, and it's done. And then so we just ask, we just have it print out the object, and it says This is ordinary non-parametric bootstrap, and it tells us, you know, so if we looked at, law, this is, you know, LSAT and GPA. So it tells us that the correlation in law is, you know, 0.776745, which is what we have here. So the Bootstrap Statistics, this tells you kind of the statistic if you applied the entire, if you calculate the correlation for the entire data set, okay? And then after it has done the run the bootstrap, it gives you an estimate of bias and an estimate of the standard error. Okay? And if you just ask for object $t, this is the results of all 2,000 kind of bootstrap numbers that you get. Your command, the function that you write here, it can return more than one statistic to keep track of. Okay, so you can kind of combine them, use C, and create like a vector of statistics to return, and you can, it'll keep track of them all also. Okay, and so so we do this, and this is basically the standard error estimate. So let me just show you the comparison here. So this standard error estimate is basically the standard deviation of all those 2,000 values that we found. Okay, so that's using library boot. You can always, I think when you're using library boot, which is optional, you don't have to do it this way. But you know, when you're looking at boot, I think the the hardest part is figuring out how to write your function to return these statistics that you want. Okay, so my recommendation is just kind of applying this, and then once you do this, then you can kind of pretend like, okay, if I've got data stored in D, how am I going to do this? Okay, but there's some good examples that are, you know, basically, you know, a lot more complicated than these simple ones in the manual pages for boot, and then you can always look for library boot R examples. And so here's a this is a good resource too. Okay, and then so there's some good examples in here as well. Google everything. Okay, and then we have you can also perform Jackknife with library Bootstrap. I know there's the boot library, and then there's the Bootstrap library, and they perform similar things, but also they're a little bit different. Okay, so there's a Jackknife function, and so here it's you provide it also a function to return the statistic that you want, but you don't subset the data. You only kind of provide it basically one a vector of values here. Okay, so in our case, we can take a look at, you know, x is 1 through 5, and then the theta that we want is just going to be find the mean. Okay, and then we just, if I just run Jackknife x theta and just see what we do, okay, what it does is it says, okay, I'm going to throw away data point 1, what's the mean of these 4, and it says, oh, okay, the mean of these 4 values is 3.5. And then we throw away data point 2, you know, what's the mean of the remaining 4, and we do that throwing away, you know, all of these things. And then when we're done, it calculates the standard error of the Jackknife, and it calculates the bias for you. Okay, so this is so that's kind of nice. You don't have to worry about the dealing with the funny formulas for standard error and bias and all of that. It is a little bit, it gets a tiny bit tricky if you're dealing with anything that's a little bit more complicated. So in our case, if we have the law school data where we have 2 columns, what we pass to Jackknife, we're just passing it basically one thing of x's, okay? So we have to expand our function for theta, okay? And the function for theta now will take the x. So the x is provided, so when you run Jackknife on this, Jackknife is going to provide kind of this resampled index of x to the function theta, okay? And so what we're going to do is we're going to take that index of numbers, and then we're going to also take a second argument. In this case, it's going to be the data, okay? And what we want this function to return is the correlation between basically when you subset x data based on the rows that x returns, then we calculate the correlation. Okay, so basically you can think of this Jackknife as kind of a wrapper for the big loop, and every time the loop runs, it's going to supply, hey, I've thrown away the first data point in x. Hey, I've thrown away the second number in x, okay? And so in this case, we're, the x is going to be 1 through 15, and we give it the function theta, okay? Now, the nice thing about the Jackknife function is it really only takes 2 functions, or I mean 2 arguments, which is basically the values, or in this case, it'll be indexes, and the function theta, okay? But then you can just tack on additional arguments, and in this case, the additional argument is x data, and it just passes it on to the function theta that it calls. Okay, so you can look up the help on Jackknife, and it says, okay, yeah, all I need is x and theta, and then any other arguments that you give it in this ... is just going to get passed along to this theta function. So because the theta function takes on x data, this x data just gets passed on into there. Okay, so we can run this, and here we go. We get the results of our Jackknife on the law school data. Okay, and so if we compare this to what we had at the actually, I'll just at the top of our lecture, we performed Jackknife on the same data set of 15 data points, and what do we see? The Jackknife estimate for bias, when we did it kind of our manual way, is exactly the same, and the Jackknife estimate for standard error over here is also exactly the same, which is expected because when we're doing Jackknife, there's no random element there. Okay, because we're methodically going removing a data point one at a time. So there's no randomness. When you do Jackknife, you're going to get the same results in all cases there. Yeah, question? Go back to the documentation of Jackknife? Sure.
So I saw that in arguments it says the x is a vector of the data.
Yeah, a vector containing
Containing the data.
the data.
Yeah, but why in the second function you define the x is actually a vector of from 1 to n?
Yeah, so because the simple version, so this version of Jackknife is just expecting a univariate kind of just a univariate thing, and if you're going to calculate, so you can only the statistics you can calculate are only the basically statistics on univariate things. So like the mean, the median, the range or whatever. or you can make it more complicated, the trimmed mean or whatever, based on a univariate thing. So if you want to do something more complex, such as bivariate data, then you have to complicate your formula and say, rather than taking the actual values of x, I'm going to supply it a vector of indices, perform jackknife with the indices, and use those kind of the jackknifed index to subset our data and return the statistics that we want from the subset data, which is what our function theta here does. Okay, so we're taking, when we run jackknife, we're giving it the basically 1 through 15, our index of values, or of rows, and then what this function does is then it says, okay, the first time I run this, I'm going to provide for the theta function x being 2 through 15. And then the second time I run it, I'm going to provide for the theta function x being 1, 3 through 15. Okay, where I've dropped the second thing. Okay, and then the next time I run it, so it's just going to take this and it's going to just remove them one at a time, and provide that as x for the theta function. And because that's not the data that we actually want to analyze, we're going to pass this extra function x data into here and use our bracket notation to subset x data and get the statistic that we want. Okay, so we could do this. We can complicate things even more. We can apply this to like linear models. How does our slope change if I perform jackknife, removing one data point at a time, things like that, and you can kind of get an idea of how all of this stuff goes. Okay, and again, the big picture here is that we're trying to make inference about the population based on the sample that we have. Okay, and we're unwilling, or maybe we can't make major assumptions about the population distribution, right? So if we could assume that the population is normally distributed, we don't have to do Bootstrap. We can just say, oh, I know properties about the normal distribution, this is how it works. But here we only have the sample, we have no other information about the population, so we're just kind of doing our best with the sample that we have to make inference about the distribution that exists in the population. Is this okay? All right, we're running out of time. Okay, so we've got okay, we'll wait till Friday to go over Bootstrap confidence intervals. Okay, because it's not that it's super exciting, but I don't want to be rushed going through it. So you should be able to at least get started on your homework. A lot of it deals with the parametric Bootstrap using known distributions. It's just try a few of these things out, and then yeah, there's just a couple questions on non-parametric Bootstrap, which we'll finish covering later this week. Okay, so we'll see you guys on Friday.